Hi everyone, Mechanics of Material, Chapter 6, Bending in Composite Section. Let's see if we do have three boxes sitting top of each other with different modulus of elasticity and handling a positive moment of M at both sides. So we want to calculate part A, maximum compression ratio of maximum compression strain to maximum tensile strain, and like in part B, maximum compressive stress, this time to maximum tensile stress, and in part C, maximum compression stress to maximum compressive strain. Let's see how we can approach this problem. The very first part is to calculate the centroid of our composite section. Y bar is summation of AI times Yi over summation of areas. And to do so, if you just consider our base like here at the very bottom, and then multiply the area, for example, this part h over 3 times length times the centroid for this part, which if you calculate the distance is this part is equal to 5h over 6 based off the given height. And the only thing we just consider here is the weighted centroid. So that's the considering the effect of modulus of elasticity of each part on the area. So that's h over 3 times L times modulus of elasticity of 1 for the very top. For 3 times E and 2 times E, we have the same, like 1E, 3E, and 2 modulus of elasticity. And then we just cancel out E and just replace the number 1, 2, now 3, 2. So that's the weighted centroid calculation. The other way is to just multiply these two, and effect of this one is project this in the height of the section and then calculate the modulus of it. This is the easier one. So if you do the math, it just gives you an y bar centroid from the base in terms of height is 4 over 9 times h. And as soon as you have that one, you do know what the centroid or neutral axis is, and then maximum compressive strain to tensile. So if your section handling a positive moment like what you can see here, definitely the farther distance experiencing the highest strain, because strain has a direct relation to, so this is the epsilon maximum tension compression, and this is epsilon max tension, because this is a positive moment, pushes the top and pulls the bottom. So this is compression zone, this is the tensile zone. And if you want to see what the numeric value of epsilon maximum C, so that's 5/9 over h over this distance, which is 4 over 9h. So if you do the math, it just gives you 5 over 4, which is this ratio in part A. And if we move to this time calculation of the ratio of maximum compressive, this time stress to tensile maximum stress. So this time it's a bit more tricky. Based off Hooke's law, we do know that the stress is modulus of elasticity times strain. So if the distance is 5 over 9 from the centroid to the very top, so you have to multiply the modulus of elasticity to that strain to calculate the stress at that point. And when you travel far down to the boundary of these two layers, in order to see the maximum, go with the higher modulus of elasticity, 3 times E times 2h over 9, which is this distance, centroid, neutral axis, or line to the location of the boundary of the two layers. And the third point is, again, if you want to go for the maximum, go with the higher. This is again the higher, 3e times h over 9. And if you move all the way to the down, go with the 2e times 4h over 9. And then you have to compare these numbers. So sigma, which is this number at the very top, this number at the interface of two layers, and again this number, and also at the very bottom. If you pay close attention, you can easily see this is the maximum stress at the boundary of two top material in terms of numeric value. So sigma maximum compression is 6h over 9, 3 times to 6h over 9 over the maximum compression, which you can easily see 8 over 9 times h, which if you do the math, it just gives you 3/4 of the ratio of these numeric value. And at the very last part, we want to calculate the maximum compression in terms of stress to maximum a tension in terms of strain. So that's definitely 6.9 over h, this number, over sigma maximum epsilon in terms of a maximum tensile, which is uh, I think this would be maximum tensile in terms of strain happened here from centroid. So that's 5h over 9. And if you do the math, it just gives you 6 over 5. And if we want to show that graphically in terms of strain, you can easily see the maximum happens at the farthest distance. If you travel all the way to the top, that's epsilon maximum in terms of tension, in terms of compression, that's a positive moment. And if you travel all the way down, that's epsilon max in terms of tensile, because it just pulls here. That's a tensile domain. And if you want to show the stress, so you can easily see there is discontinuity in the boundary layer. So it says all the time maximum stress doesn't occur. So this time it occurs at the very bottom, but sigma maximum in terms of compression occurs in the boundary of the two materials. So that's an important note. So it is obvious that the maximum, extremums, maximum or minimum values for a strain definitely occurs at the top or bottom, but for in terms of external maximum and minimum for stress, we must also double check the boundaries. So it can happen at the boundary layer, at the farthest distance, but at the same time we need to double check. For example, for sigma maximum tensile, it happens at the very bottom of the section, but sigma maximum for compression, you can easily see it doesn't happen at the very top part, but it happens at the boundary layer. So for the boundary, for stress, we do need to double check also the boundaries layer, including the uh, farthest distance from the centroid as well. We'll solve more problem in composite section. Thank you.